G'day, in this video we're going to look at acceleration of a projectile in the horizontal and vertical direction and look at some key assumptions which will allow us to apply kinematic principles when completing projectile motion analysis. So again, these techniques that we're learning about help us to address dot points 5.1, 0.1, and 4. Primarily, we're starting to kick into the first dot point, which looks at the analysis of motion of projectiles by first resolving the motion into horizontal and vertical components, which is what we did in the previous video, but then also using the assumptions that a constant vertical acceleration occurs due to gravity and that there is zero air resistance. So our learning intentions for today is to first unpack factors which could influence the vertical and horizontal acceleration of a projectile in flight, and then apply these accelerations of the projectile to the V equals U plus AT equation, and then we'll have a look at completing a quick practice calculation. So when we connect horizontal acceleration and resultant velocity, we should first take into consideration that there are many factors which could influence the horizontal acceleration of a projectile. Primarily, we'd be looking at air resistance, but potentially a tailwind could be present, or an external applied force of any other kind could be influencing the horizontal acceleration of the projectile. However, it's really important in this topic that we assume that these factors are not applied. This would make the problems a lot more complex to solve and is not a requirement of this course to apply concepts like air resistance to our solutions. As a result, we need to assume that A, or acceleration, in the x direction is equal to 0 always. As such, if we apply this assumption to the V equals U plus AT formula, knowing that AX is equal to 0, this will mean that the second term in the right-hand side of the equation is eliminated, meaning that Vx is actually equal to Ux. In other words, at all points of flight, the horizontal velocity is constant. In the diagrams that I have on the right, I wanted to show how the trajectory begins to change with air resistance or without it. As we talked about in the previous video, we assume that all projectiles behave in a parabolic way, that their trajectory forms a parabola, and this is caused by the fact that we are removing air resistance from consideration. However, with air resistance, the horizontal velocity will begin to decline as the projectile moves through space, and thus there is a little bit of a drop-off that occurs as the projectile starts to fall back down to the ground. Without this air resistance, we would expect that the trajectories would extend much further outward than what's being shown in the graph. However, there is acceleration that we need to take into account for the vertical axis, and that factor here is gravity. Technically, we could also be focusing on other applied forces or resisting forces like air resistance, but similar to the x direction, we are going to ignore them. The only acceleration that the projectile is expected to experience is the acceleration due to gravity, where g is equal to negative 9.8 meters per second square. So when applying this to our V equals U plus AT formula, we know that the acceleration due to gravity, negative 9.8 meters per second, can be written as g. We can rewrite an equation for the V equals U plus AT formula in terms of the y-axis by writing Vy equals Uy plus gt. Something else that I want to highlight in this video in particular is U and V and how we use them in kinematic equations and what they actually mean. Previously, we learnt and talked about the concept that U and V were essentially initial and final velocity, both of which are instantaneous velocities and should not be confused with a calculation for average velocity at any time. It's probably more appropriate to define V as velocity at a given time. What that means is there are many velocities that we could calculate for this projectile as it moves through its trajectory, because its instantaneous velocity will be continuously changing. So for example, if we were to use the V equals U plus AT formula, we could calculate the velocity of an object after 2 seconds, which would be calculated as U plus 2a. Similarly, we could calculate for the velocity after 10 seconds by applying the U plus AT formula. In this case, it would be U plus 10a. This concept continues to make sense as we reflect on the behavior of the equation when t equals 0. Essentially, if t equals 0, then we have the initial velocity. And that is reflected in the equation because when we substitute in v is equal to u plus 0a, eliminating the second term, meaning that v, the velocity at time 0, is equal to u, the initial velocity, which is the velocity that we expect at t equals 0. So for this video's practice question, we have the same scenario as we did in the first video. A ball is being thrown at a launch angle of 48 degrees and has a velocity of 2.5 meters per second. We're being asked to determine the horizontal and vertical velocity of the ball at 2.5 seconds after the ball was thrown. So here on the left, I've just included the calculations that we did in the first video to determine the initial velocities in the x and y direction. From here, we can apply kinematic equations to determine the velocity in the x and y directions after 2.5 seconds have passed from the launching of the ball initially. In order to do this, we will need to use v is equal to u plus at. Let's have a look at the x direction first. So vx is equal to ux plus at. And we know that ux is approximately equal to 17 meters per second. We're also going to assume that ax is equal to 0 because we're assuming no air resistance needs to be taken into account. And finally, we've been given t is equal to 2.5 seconds. Given this data, the second term in the equation, at, can be cancelled out as ax is equal to 0. As a result, we can say that the velocity in the x direction at t equals 2.5 seconds is going to be equal to ux, which is approximately 17 meters per second. Now in the y direction, the calculation is only going to be a little bit more involved than the previous. Again, we're going to look at this idea that vy is equal to uy plus ayt. Extracting our data, we know that uy is approximately equal to 19 meters per second. We know that ay is equal to g, which is negative 9.8 meters per second square. And finally, in the question, we've been given that t is equal to 2.5 seconds. So when calculating for vy at t equals 2.5 seconds, this will be uy plus gt, which is 19 meters per second plus negative 9.8 times 2.5 seconds. Note that when we put in these values into the calculator, I'm going to put in a saved value for uy, which I saved into my calculator when calculating for the previous question. Another way that you could do this to make sure that we're not putting in rounded values is to substitute in 25 times sine 48 into that uy component of the question. The result that we should get is negative 5.9 meters per second. Now, given the velocities that we have, what we should be able to assume is that after 2.5 seconds, the ball is somewhere roughly here in its trajectory. Because what we've been told is that Vx continues to be about 17 meters per second, and that Vy is in the negative direction, which reflects the ball going downwards and is approximately equal to negative 5.9 meters per second. What this will mean is that our V value will look something like this, where the velocity is now pointing still towards the left of the page, but is moving in a downward direction. When we have velocities which are angled below the horizontal, we can assume that the projectile is moving in the second half of its trajectory and is making its way back down to the ground. Thank you very much, everyone. In the next video, we'll continue to apply some of the concepts that we've learned in the last couple of videos to look at another kinematic equation, which will allow us to calculate the position of a projectile at any given time. But until then, have a good one.